very much for an opportunity to speak at the seminar. I would like to discuss our recent works where we calculated some subsystem entropy in different conformal field theories. But I will start my talk from maybe a historical overview. So here is the plan of my talk. I want to spend first part of the talk talking about the diagonal approximation, what it is. The roots of this approximation is in semiclassics. It happens to be a very powerful method to calculate subsystem entropy in different regimes. I expect that at least a third of my talk will be covering this historic part. But if that is covered, then we will try to apply this method to CFTs. And then if time permits, I will try to talk about our recent paper where we actually did some calculations for two-dimensional conformal field theories, which we consider to be in the states with the chemical potentials for additional conserved quantities called quantum Kordovec de charges. Okay, so first, the diagonal approximation. What is that? We will start with some standard statistical mechanical setup, something like in this favorite book of mine, the Thermal Physics textbook by Kittel, and we will consider a system which is split into two parts. So this is some spin chain, if you wish, or another physical system, a reservoir with gas, and we split it into two parts, A and A bar. Okay, we will assume, as it is usually done in statistical mechanics, that the system is sufficiently large. So quantities which are extensive, entropy or energy, they will be dominated by the volume of parts A and A bar, and they will not be dependent too much on the boundary, because boundary is only proportional to the area. So basically I have a volume, which is a volume of subsystem A and volume of its complement. The fraction of the fraction I will keep fixed, and I will take the volume to be very large, the standard approximations. And then I will say that my full system has total energy E, and that is fixed. So that's exactly how microcanonical ensemble is defined in statistical mechanics. And then statistical mechanics, classical statistical mechanics, is actually a little bit quantum, because people talk about microstates, and they try to understand what is the probability of a microstate of a subsystem A. And to calculate the probability of a microstate of a subsystem A, they need to calculate the number of microstates of the subsystem A bar, the complement of A, such that the energy balance is preserved. So classically, that doesn't make sense because there is no notion of a microstate classically, but we can do things quantum mechanically. So this will work well if we have some semi-classical physics. We will say that the full system, let me try to turn on pointer. Sorry, I'm slow with the. I was trying to show. I'm trying to turn on a pointer on the screen. I'm not sure how to do it. Let me just use the regular pen. So I will start with a system in an eigenstate E. And my reduced density matrix will be defined by this formula. My full system could be either in the eigenstate or in the microcanonical ensemble. And then I will assume that I can define eigenstates of a subsystem. So if I have a spin chain, or if I have any discrete system, then I can have a Hamiltonian, which is a sum of two Hamiltonians. And the interaction term is not important because it is not extensive, it is intensive, it is proportional to the area. So the curly E are eigenstates of the Hamiltonian HA. And then I want to ask, what is the probability to find my subsystem A in a particular eigenstate? And the formula is very simple. It is proportional to the number of microstates of the complement. So omega is the total number, is the density of states. Okay, so as a result, I have this nice formula, which is completely semi-classical, and it tells me that if my full system is in the microcanonical ensemble, the probability to find the subsystem in a particular microstate is proportional to the density of states of its complement. And you can see that this formula passes a basic consistency check. If you try to take a trace of the left-hand side, and reduced density matrix must have trace equal 1, on the right-hand side, you will have something like an integral of this quantity multiplied by omega A E, an integral over B. And then you can do this integral using saddle point approximation. And from this identity, which shows that entropies are extensive, and the total number of microstates is basically the contribution of microstates of the subsystem A and its complement, you will see that approximately the reduced density matrix has trace 1. Okay, so this is all completely standard and there is nothing new about it. So we started thinking about that about 10 years ago, but we asked the following question. What if your system is chaotic? If your system is chaotic, then there is an expectation that an individual energy eigenstate will behave more or less like the microcanonical ensemble. And there is a significant evidence for that. And usually this idea is called the Eigenstate Thermalization Hypothesis. Here's a slide with a historic overview. The Eigenstate Thermalization Hypothesis is usually presented as an ansatz for the matrix elements of some local operator. And we're interested in the diagonal part, which basically tells you that if you're measuring a local operator in an energy eigenstate, then the result will be thermal. So there are different philosophies here and different ways to look at the Eigenstate Thermalization Hypothesis. One way to think about it, that this is a statement about matrix elements. And if you try to translate it in the language of CFT data, that will be the statement about OP coefficients. But actually, if you focus on two-dimensional field theories, and that will be my focus today, there will be two slightly different statements. One could be about statistics of operator product expansion coefficients, and another will be about the thermality of eigenstates. So these are two slightly different statements. The statement about statistics of OPEs is a very popular topic because it gives an opportunity to connect CFTs with holography. But I will be discussing a more purist topic about thermality of individual energy eigenstates. So keeping that in mind, I also want to illustrate how things work, not so much in a CFT, but in a spin chain. Just an example, if you have an integrable spin chain, then the diagonal matrix elements of a local operator in an energy eigenstate, they're actually not fixed by anything, and they vary dramatically from an eigenstate to an eigenstate. This is a picture here. But if you consider a system which is chaotic, which doesn't have extensive number of conserved quantities, then the diagonal matrix elements actually form a very nice smooth curve here. And that is a prerequisite for those values to be thermal. So this is just an evidence, a numerical evidence, that when the system lacks extensive number of degrees of freedom, then individual energy eigenstates are thermal. So let's go back to the original idea that I have a system split into A and its complement. And now I will consider a system in the individual energy eigenstate. And I want to say that my system is chaotic. So first of all, we can formulate what we call the subsystem ETH. It's a statement that if you consider reduction of this eigenstate to a subsystem A, and you consider two eigenstates E and E prime, and their energies are sufficiently close, then corresponding density matrices will be sufficiently close as well. And this proximity, in terms of the trace distance, it will be exponentially small. And then from here, it will follow automatically that the reduced density matrix of an individual eigenstate, it is approximately equal to the reduced density matrix of a microcanonical ensemble, and we can repeat the same considerations which we just did a few minutes ago for the microcanonical ensemble and the semi-classical approximation. And basically, we end up with the following formula for the diagonal matrix elements of a reduced density matrix. We can write it slightly differently. We can write that rho A, a reduced density matrix, is the sum over all eigenstates of a subsystem. The subsystem doesn't have to be small. And then I will have this coefficients here. Okay, you can ask, is that all I can say about this matrix? This matrix is likely not diagonal. It probably has off-diagonal matrix elements, and it certainly does. But in the semi-classical approximation, those off-diagonal matrix elements will be small. In fact, this is consistent with the standard ETH ansatz, which tells you that off-diagonal elements are exponentially suppressed. So individual off-diagonal matrix elements are very small. They're suppressed. They will be very important if you try to discuss dynamics, especially out of equilibrium dynamics. But if you want to discuss something, some properties in equilibrium, for example, the subsystem entropy, then the idea is that you can ditch them. You can completely forget about them. You can pretend that they're not there and simply use this formula as your formula for the reduced density matrix of an individual energy eigenstate. And then you can use this formula to calculate von Neumann or Rényi entropy just by plugging this formula for the density matrix in the expression for the entropies. And then to really appreciate the power of this formula, I want to mention that the only thing you need to know to use this formula is the density of states of your full system and the density of states of your complement. Okay, so we will see a lot of examples in case of a CFT, but if you deal with systems where A and A bar of different nature, A bar is a reservoir of gas and A is a bunch of spins or something like that. If you can calculate the density of states of those parts individually, you can still use this formula. And I didn't derive it rigorously. It was more like a heuristic derivation. But the expectation would be that this formula will give me extensive part of the entropy because I derived it by assuming that my subsystem is large and its complement is large and the area between them doesn't matter too much. So I'm only capturing the extensive part of everything involved. Okay, it's a very interesting question how to go beyond the approximation when I'm only capturing the extensive part. And quite frankly, I do not know how to do it rigorously. So that's an open question. But so far, I'm concerned with the extensive part of the entropy. This is my formula, and it will give me amazing predictive power. So let me actually stop for a second and ask if there are any questions. Do we allow questions?
Yes, of course.
Are
there
any questions about this? Because this is maybe the most important. It's not technically involved, but this is conceptual, the most important part of my talk, how this diagonal approximation, where it's coming from. And then already in this paper, which was put out almost 10 years ago, we said, okay, let's try to apply this diagonal approximation to two basic scenarios. You can assume that your full system is in the eigenstate or in the microcanonical ensemble. For the chaotic systems, that wouldn't matter too much. You basically use the formula from the previous slide, and instead of the densities of states omega, I use entropies, where entropy is literally the natural logarithm of the density of states. And then you have this nice integral, which calculates the reduced density matrix. And then you can simplify this integral by doing the saddle point approximation. And as a result, you will have the following formula for the reduced density matrix. This is the final result. You can also play the same game for the canonical ensemble, where your global state is E minus beta H. This is a canonical ensemble or Gibbs ensemble or thermal state. Different people call it differently. You can apply the formula from the previous slide with the only difference is that you have to integrate with the weight eta E minus beta energy and integrate over the energy of the full system. So if you do that and use the saddle point approximation, the resulting formula for reduced density matrix of a canonical ensemble will be slightly different. So these two formulas, they are different. And that's the whole point, that if you have a full system in the microcanonical or in the canonical ensemble, the reduced density matrix will be different. You can ask if perhaps that violates the standard result in statistical mechanics about the equivalence of ensembles. And I will tell you that it doesn't, because usually the equivalence of ensembles is discussed in the context of a small probe. If your probe is small, it means that your subsystem A is very small. And if so, energy E, curly energy E, is very small in comparison with the energy of the full system. And you can try to expand here in terms of the small energy E. And if you do that, you will immediately obtain this formula. Okay, so that will restore the equivalence of ensembles. But if your subsystem is large, comparable with the full system, so the fraction, the coefficient f I introduced here, that's a fraction, it will be fixed, could be 0.1 or could be 0.1, doesn't matter what it is, but it is fixed and it is not enormously small. Then those two formulas will give you different results. If you try now to calculate the entropy of a subsystem, it will be interesting, because if you try to calculate the von Neumann entropy, interestingly enough, both of these formulas, although they're different and the density matrices are different, will give you exactly the same von Neumann entropy. So even though the subsystem doesn't have to be small. So the extensive part of von Neumann entropy doesn't distinguish between microcanonical and canonical ensemble. But if you try to calculate the Renyi entropy, for which you will need to take this matrix or this matrix and take it to the power n, Renyi entropy will distinguish between those two. So that was our conclusion in this 2016 paper. Basically, this is a starting point for my talk today, because now what I can try to do is to consider different physical systems. And so far, I know entropy of a subsystem and its complement. I can calculate a lot of things. So before I do that, I can make a comment that if my system is translationally homogeneous, something like a spin chain or a field theory, then the density of states or thermal entropy of SA or SA bar or S of the full system, it will be given by the same formulas, because these are extensive parts of the entropy, or if you wish, entropy densities. And entropy densities in the translational invariant system, they have exactly the same form. Right? And therefore, if my system is homogeneous, I'm not trying to couple the reservoir of gas to spins, I'm just considering spins or the reservoir of gas split into two, then I actually only need to know how my thermal entropy or density of states depend on quantities such as energy density and stuff like that. Okay, so now let's try. Sufficiently large. Physics-wise, yes. If I will be discussing CFTs in a second, and in the case of a CFT, there is a subtlety, because if I have a spin chain, I can say that my Hamiltonian is HA plus HA bar plus H interaction. And then I can define an eigenstate of a subsystem, and you can choose H interaction, whatever you want. In case of a CFT, there is it's more difficult to argue rigorously how to do that. And actually, we do not argue for that in our papers. We simply say, let's go, assuming let's just get to the result, assuming you can do that. I think it's an interesting question, how to put it on a rigorous footing. and try to define the subsystem Hamiltonian for the CFT and the eigenstates of those Hamiltonian. Okay. Okay, so now part number 2 of this talk. Let's try to apply this formula to CFTs. And in case of CFTs, everything is very, very simple because entropy is an extensive quantity. The theory has no internal scale. And therefore, it must be that the entropy as a function of a volume and the function of energy has to be proportional to the volume and the intrinsic property characterizing energy density, which is temperature. So this formula is automatic for all CFTs in all dimensions. The coefficient kappa will be model specific. In 2 dimensions, I can relate it rigorously to central charge. I don't remember the exact coefficient. It's written in the paper. Kappa is something like C divided by C pi divided by something. I don't want to waste time looking at my notes. In higher dimensional CFTs, there is no such universality. There might be some results about supersymmetric models, but there is no such universality. Kappa is not necessarily related to something like A anomaly or C anomaly or any other definition of a central charge, but any CFT has such a coefficient. Okay, so then all you need to do is to start with this formula, write it in terms of the volume and energy. And again, this is all fixed by dimensional analysis. Next, we assume that that is an assumption in the CFT that you can define the subsystem eigenstate. And then you basically apply the formulas from above. You take this matrix or you take this matrix, and you plug them into the formulas for the von Neumann Arrhenius entropy, and you calculate the integral using the saddle point approximation. So it becomes a very simple algebra calculation, and you immediately can get a result for subsystem Arrhenius entropy in our thermal state. By thermal state, I mean the Gibbs state. The Gibbs state or canonical ensemble, or you can do the same for the microcanonical ensemble. And we calculated that in the paper. Of course, as at the level of answer, these are not new results. These results we obtained, first of all, we can trust them only at the level of extensive contribution. So something proportional, entropy of origin A, proportional to the volume of origin A and the coefficient, then you have corrections which are area-like, and we cannot capture them, at least with the current technique. And these answers, they match earlier works, which include holographic calculations. And I hope to be able to say a few words about holographic calculations, where people use essentially the same approach, the diagonal approximation, which is known under the name of fixed area states. But the math is essentially the same. So the calculation actually, not only the result is the same, actually the calculation is the same. So there is a way to justify this diagonal approximation holographically. And there are, of course, earlier works, not only holographic, but in cases like 2D CFTs, people know Cardi and Calabrese calculated Arrhenius entropy for canonical ensemble, and there are also calculations in particular models. So all the results we know of, we match, right? Maybe the added mileage here is that instead of working very hard, we obtained it almost for free. So the calculation was essentially trivial. Okay, so
also for you, it's more general, right? You don't assume holography. You just assume
absolutely.
some extent of chaos. So you don't assume maximal chaos. It doesn't matter.
You're absolutely right. We don't accept, oh, excuse me, we don't assume holography. So results a little bit more general. Actually, if you want to calculate the result for the microcanonical ensemble, you do not even need to assume chaos. And we know that some of the results of Cardi Calabrese, those results which are exact, they're for any CFTs, including integrable, and we reproduce that, right?
Okay.
The question is whether this microcanonical result will also give you the eigenstate subsystem entropy. And here you probably would expect that this will only work if your model is chaotic.
Can you explain why? I actually don't follow the last one.
Because if your model is not chaotic, individual energy eigenstates
So
could be
exactly for that reason. So, but oh yeah, the density of states does not care because you said that the density of state will be reproduced even in non-chaotic systems.
The density of states is usually the same for chaotic and non-chaotic systems.
Okay.
The level repulsion, or what is called the two-point function of density of states, cares about chaos, but what is called the one-point function of the density of states usually doesn't. And therefore, you can use my formula and get the result, but it will be correct result for an average quantity for the microcanonical ensemble. It might not work for an individual energy eigenstate.
Okay, thank you.
Okay. So actually, if we go this route, we can say, okay, into the CFTs, there are energy eigenstates. Primary states are energy eigenstates. Let's try to calculate something about them. Okay. And now we are going slowly into a third part of my talk, that we will slowly need to see that to describe individual energy eigenstates in 2 dimensions. The results on this slide, they're for any dimensions. If you take d equal 2, you will get 2-dimensional result, but they're more general. But in 2 dimensions, we can try to calculate something for primary eigenstates. And there are several calculations in the literature. One calculation was done by Tom Faulkner and Hoajia Wan in 2018. And Hoajia is a collaborator on these papers I'm talking about. So he basically pioneered this puzzle. I will try to explain to you. And in 2018 they calculated the subsystem Renyi entropy of a primary state in 2D CFT. And they got this result. The only subtlety is that they didn't get C-1 here. Instead of square root of C, C-1, they only could get C because they were calculating things that lead in order in C. So this formula on the slide is a little bit more precise than what they got, but that doesn't matter. What matters is that they got this result, and this result is independent on the index. Okay, so left-hand side, it's a Renyi entropy. It depends on the Renyi index n. Right-hand side doesn't depend on the Renyi index n. It's a very peculiar behavior of a primary eigenstate subsystem entropy. And you can worry, maybe they made a mistake. Well, they didn't make a mistake, but you can worry if their method is correct. Their method, by the way, was a completely different one. It was based on what is called the monodromy method. So they were calculating something precisely for 2-dimensional CFTs. You can try to reproduce the result using the diagonal approximation. This is what we did in the paper. To do that using the diagonal approximation, you actually need a little bit of an embellishment of the diagonal approximation, which I will try to explain later in the talk. But let's say you somehow manage to use the diagonal approximation to get the result. This is what you get. You again don't get any index dependence. And again, this calculation, you need to compare it with what you know for microcanonical ensemble in 2-dimensional CFT. And microcanonical ensemble was first considered by Shidon using holography, but now we can reproduce that result not only in the infinite C limit, but for finite C using the diagonal approximation. This is the microcanonical result. And it doesn't match the primary state result at all, because the microcanonical result has very explicit n dependence. You might think for a second that maybe the right way to compare is the primary state should be compared with the canonical state. That it will not help. First of all, the canonical state, this is a Cardy-Calabrese formula, it also has n dependence. And second, a careful consideration of the kind I did in the beginning of my talk will tell you that the eigenstate should be compared with the microcanonical state, not the canonical state. So basically, you try to compare this and this, and they do not look the same. The only instance, when they look the same, there are two instances. If you consider von Neumann entropy, n equal 1, or you consider arbitrary n, but very, very small subsystem. Okay? So what is the conclusion here? One possible conclusion is that Eigenstate Thermalization Hypothesis is violated. It's not satisfied in two-dimensional CFTs. And certainly it's not satisfied in those CFTs which we understand well and control well. Let's say a minimal model or a free scalar or something like that. These are integrable models in a conceptual sense, so we don't expect ETH to be satisfied. But what about holographic models? Those we do not fully control on the field theory side, but we expect them to be chaotic. So this is very unsettling. And that remained more or less like a puzzle, though we had a conjecture back in 2018 how this is supposed to be resolved, but we only were able to see that this is exactly, that it works this way in this recent paper, which we wrote with Hodge and his students more recently, this paper, which this talk is based on. So now we have a puzzle. Let me try to move on and explain how this puzzle is resolved. So to resolve this puzzle, I have to actually go back and revisit ETH in case of two-dimensional CFTs, and I need to understand that conventional ETH indeed doesn't work. This discrepancy we saw between the microcanonical ensemble and the primary state, that's a genuine discrepancy which tells you that ETH in the plain sense doesn't work. Individual energy eigenstates are not necessarily thermal, okay? Well, it doesn't mean that things are incomprehensible. It just means that you need to take into account that two-dimensional CFTs, all of them, have an integrable sector. They have conserved quantities. So if you want to be a little bit abstract and think about, I don't know, integrable spin chain, the conventional ETH at the level of the diagonal matrix elements will be formulated like that. You will say that we already saw this formula, just so I'm rewriting it in a slightly different way, that individual energy matrix elements, diagonal matrix elements of a local operator in individual energy eigenstates, they are thermal. So this function is just the thermal expectation value of your operator. What will happen? And from here, you can conclude that if it applies to all operators A, then your individual energy eigenstate is thermal. What will happen if your system, let's say a spin chain, has many conserved quantities, extensive number of conserved quantities? All of these quantities are conserved, not only energy. Energy is one of them. I will call those quantities Q. Energy will be Q1, but there will be a tower of extensive quantities. If they're all conserved, whatever thermalization you're expecting to occur, it will not change those quantities. So your thermal ensemble cannot be just the conventional Gibbs ensemble. It has to be something like generalized Gibbs ensemble, where you have exponent with all the chemical potentials and all of these relevant quantities. So basically, your thermal expectation value is not only a function of effective temperature or energy density. Temperature and energy density, these are Lagrange related to each other. But in fact, your thermal equilibrium now depends on the densities of all charges Q, or many of them, most of them. That could be a tricky question to answer, but by default, we should include all of them. Or equivalently, instead of one temperature, you should introduce a lot of chemical potentials, and your thermal state will depend on all of those chemical potentials. So now the generalized Eigenstate Thermalization Hypothesis should look like this. Diagonal matrix elements of a local operator. These are smooth functions of the densities of the conserved quantities. And if there are many such quantities, you should include all of them. This is a very standard framework, which was introduced almost 20 years ago, around the time when the conventional ETH came to prominence. And basically, what you're supposed to do if you have an energy eigenstate, you should calculate all the conserved quantities associated with that energy eigenstate, divide that by volume such that you will have the density of states, and then this quantity F will be the function of densities of those quantities. So that's a new version of ETH. And in that case, you will expect that the reduced density matrix of an individual energy eigenstate, it will have some universal form, but it will be a function of density of states. Now, the question is, what kind of relation this has to CFTs? Apparently, in two-dimensional CFTs, there are always conserved quantities. And in two-dimensional CFTs, there are primary states and there are descendants. And primary states will be denoted like this. And descendants, you just act by Virasoro generators. And these are additional integer numbers on top of the primary, which tells you what kind of state you have. The energy of a state is an energy of the primary plus the level of a descendant. The density of states can be counted individually for the primaries and for the descendants. For the descendants, is just the number of decompositions of integer number n integer sum. Basically, you're trying to find the number of integer partitions. But that's not the full story. At the level of CFT Hamiltonian, many descendants have exactly the same energy. The CFT Hamiltonian is very badly degenerate. It's very badly, that, of course, nothing new about it. It's just when people talk about thermalization and two-dimensional CFTs, this is somehow quite often overlooked as something unimportant. But if you care about actually thermalization dynamics in two-dimensional CFT, it's important to understand that CFT Hamiltonian, which is L0 minus C over 24, it's very badly degenerate because all the descendants at a particular level have exactly the same energy. And even though you expect that in a chaotic CFT, deltas will repel each other, there will be level repulsion at the level of deltas, they will be all different. Still, the descendants of the same delta, they will be degenerate, and therefore you might have non-thermalizing dynamics. You can have very heavy descendant states, which will never thermalize. They will just rotate forever. The energy is quantized, n is an integer number, so you will have sort of periodic motion. You can even discuss that in ADS. You'll have some periodic motion in ADS. It will never thermalize. It will be oscillations forever. Okay? And the counterpart of that is that in addition to the energy, the Hamiltonian L0 minus C over 24, in addition to the charge Q1, there is an infinite number of conserved charges, which are all extensive quantities. They are built out of stress energy tensor. Only for some tradition, they're labeled by odd labels. There is no Q2, there is no Q4. There are Q2 and Q4, but they're unrelated. They're not, we don't care about them because they're non-local. We only care about local things, Q1, Q3, Q5. There is an infinite tower of them. Q5 is proportional to T cubed plus some corrections. They're very complicated expressions. If you try to write them in terms of the Virasoro generators, they're crazy complicated. That doesn't matter. What matters is that there's a conserved quantities. They exist in any two-dimensional CFT. They all commute with each other with the Hamiltonian, and therefore there is an integrability structure in the stress energy tensor. And basically, what I'm trying to say is that we need to carefully take these charges into account if you hope to have the correct version of ETH. So what we were able to do, it's not in a historical way, but what we did more recently, we were able to solve this quantum hierarchy in the large central charge limit. So we know the eigenvalues of these charges, and to some extent, we know how to build the eigenstates. That will be an overkill because for us, the most important thing will be to formulate the generalized eigenstate thermalization and also calculate the free energy. And that was done a little bit earlier with some heuristic guesses. So I don't expect you to pay too much attention to these explicit formulas. I just want to convey a message that there is an integrable structure. It's complicated. It can be solved in the thermodynamic limit when you consider either very large volume of your CFT, or equivalently, you can shrink your CFT to be of size 1, but then the energy states will be very highly energetic. And then you additionally take central charge to be large and you do formal expansion of solar charge, we were able to find things, first few terms in the expansion in 1 over central charge.
Can I ask, why do you say these non-local charges, why do you throw them away? They're not going to participate in the thermalization dynamics, or just because they don't? That's the question.
The question was why
The non-local charges, yes. You're saying you're only considering the local charges? Yes, I know. So they don't participate in thermalization, or they're not important for your arguments?
They're not supposed to participate in the thermalization. They're not supposed to.
Not supposed.
They're not supposed to. That might be a bit of a tricky question. I think there was a lot of discussion in the context of integrable spin chains, which conserve quantities to include. There was some breakthrough in the XXZ model around 2014, when I think there was a work by Tomasz Prozin and collaborators when they understood that unless you include semi-local conserved quantities, you will not be able to describe the equilibrium correctly. But non-local things don't have to be included. That is the consensus, which is based on analytical and numerical results in an XXZ chain. We just say, let's consider just Qs. And then in the large C limit, when we have analytic control, I can show that Qs is sufficient. I will basically formulate generalized ETH, solve it, and I will get away just with Qs. If you tell me that when C is finite of order 1, I need to include other things, I will not believe you, but I will not have any rigorous argument to rebuff. I will say, okay, maybe. Okay. So that's the status of this. So now we can return back to the microcanonical ensemble in two-dimensional CFT. And we have basically two important quantum numbers. We have the primary and the level of the descendant. And we can try to calculate what is the typical state inside the microcanonical ensemble. And if you look at it, that's a very simple calculation. All you need to know is the Cardy formula and the formula which calculates the number of integer partitions. I think this is called Hardy-Ramanujan formula. But by now, this is all very well understood. Wikipedia knows these formulas. You use them. You calculate things using subtle point approximation. And you see that if you fix energy density, effective temperature fixes energy density, then you have certain primary and you have certain descendant. And if your size of the system goes to infinity, I'm considering it's a CFT. You can always take the spatial circle to be of order 1. But I prefer to think of it to be very, very large and the energy density to be finite. You can always consider it to be 1, but then the energy density will diverge, right? Because there's only one parameter here. Beta is the only dimensional parameter. Or if you want to introduce length, then beta divided by length becomes dimensionless. So if you consider the thermodynamic limit, then you will see that the descendant is also non-zero. So it tells you that the typical state in the microcanonical ensemble is a descendant of a very, very high level. And if you try to calculate those conserved quantities Qs, you will see that the typical state in the microcanonical ensemble, of course, will have exactly the same Qs as the microcanonical ensemble itself. But the primary state will have different Qs. And therefore, we realized early on, already in 2018, that if you formulate ETH including Qs, then you have a way to resolve the puzzle, because the primary state, you don't have to compare it with the with the microcanonical ensemble anymore. Because those two states, or two different ensembles, microcanonical ensemble and the primary state ensemble, those two ensembles have different densities of Qs. And therefore, if you want to match them to generalized Gibbs ensemble, you will match them to generalized Gibbs ensembles with different chemical potentials. You don't need to compare them. That's not the proper thing to do. So you resolve the puzzle by changing the question. Okay, so that was the idea in 2018, and we were reasonably confident that this is how it's going to work. But now we did the calculation, and I'm happy to tell you that this is exactly how this is working. And the rest of the talk is 15 minutes or 10 minutes. I will try to give you some of the details. So first step is to formulate the generalized ETH, and it is formulated this way. You consider a local operator, you consider it in an energy eigenstate, which is not a primary state. It's a primary state and descendants, and you don't control. You need to consider all possible descendants. And then you ask, what is the expectation value of that local operator? And basically, if your local operator is a descendant of an identity, so it's something made out of T-minus, then you can actually find an explicit expression. It's a polynomial expression, which is a function of densities of the Q charges. In the first leading order, non-trivial order in 1/c, we were able to find those polynomials explicitly, and we were able to match those matrix elements to the smooth functions of Q. So that establishes that there is a generalized ETH, and that also establishes that no other charges are necessary because we already fitted the left-hand side with the smooth function of Q. Okay? You can ask me why I'm only considering the descendants of the identity. Well, this is presumably the only thing which matters, because if you consider operator A, which is a primary, then the thermal expectation value of a primary is 0 in any CFT. And this is because a thermal expectation value is a one-point function on a thermal cylinder. In 2 dimensions, thermal cylinder is conformally flat, and therefore you can calculate this one-point function on a flat surface or on a plane, and it has to vanish. Now, that establishes that any primary has 0 vanishing thermal expectation value. That doesn't establish that expectation value of any primary in an energy eigenstate will be 0. That is the statement of ETH. But that is a statement which we expect to be true at the level of OP coefficients. You need to calculate corresponding OP coefficients. This is something we discussed with Nima Lashkari and Hong Liu in a 2016 paper, which is something like Eigenstate Thermalization Hypothesis in conformal field theory. And the idea is that you can reformulate the statement that individual eigenstates will have 0, primary states will have 0 expectation value in any energy eigenstate. That expectation value will that expectation will boil down to the statement that certain heavy light OP coefficients have to vanish. And unfortunately, there is no way for us to probe that or check it. This is a conjecture. So if this is not satisfied, it means that ETH has to be thrown away out of in the window. But we expect, and many other people think that this is accurate, they expect exactly the same thing, that in a holographic CFT, that will be satisfied. So that will be satisfied. So if this will be satisfied, the only thing you need to worry is if A is a descendant of identity. And then for the descendant of identity, you cannot have conventional ETH. You have to include those Qs because you can calculate this function and see that this is an explicit polynomial, which includes not only Q1, not only energy density, but higher Qs as well. Okay, so now we have a proposed resolution, which I already announced to you, that we will not compare microcanonical state and the primary state. We will not compare them with each other, but we will try to match them with different GG ensembles, where those GG ensembles include KdV charges. I don't have too much time, so I probably need to decide what I want to tell you. I maybe want to tell you what we did in the paper without actually telling you the details. In the paper, we did the following. We used a result which we calculated previously for the free energy of the generalized KdV, generalized Gibbs ensemble. And using that result, you can basically calculate entanglement subsystem entropy, subsystem entropy when the full system in the KdV GG ensemble. And the expressions, there are many explicit expressions, but they are usually ugly. An interesting thing is that there could be very non-trivial dependence on the index, but there are also a possibility to play with the chemical potentials. And if you consider generalized Gibbs ensemble with only 2 KdV charges, this is energy, this is L0 minus C over 24, and this is the first non-trivial KdV charge. This ensemble already will interpolate between the canonical ensemble, that's easy, canonical ensemble, you take mu3 equals 0, or it can interpolate to the primary state. And to interpolate to the primary state, you need to consider a very non-trivial, well, slightly non-trivial limit. You need to take mu1 to be minus infinity. If mu1 is minus infinity, you might worry that your exponent will not be bounded from below, but everything will be fine because Q3 will always grow faster than Q1. And if you keep mu1 and mu3, their ratio fixed, then in this limit, you will recover primary state as a singular limit of a generalized Gibbs ensemble. And then you apply the extension of the diagonal approximation. The diagonal approximation has to be extended. Instead of the density of states which know about the volume and effective energy density, you need to go into formula which knows about volume. That volume is easy. Volume is always factorizes. And here you will have densities of KdV charges. But this function can be calculated because we know free energy for different KdV charges. Okay, so that was our result. We calculated path. We calculated this partition function of a generalized Gibbs ensemble. Trace E minus beta H minus mu Q. You can calculate this thing. We calculate it in the large C limit. Once you calculate free energy, you can recalculate density of states. And knowing density of states, you can apply diagonal approximation and calculate the subsystem entropy. And in the end, you have different GG ensembles. Some of them will match exactly the primary state. Some of them will match exactly the microcanonical. Some of them will match the conventional microcanonical ensemble. We also extended these results by calculating subsystem entropy of what is called KdV microcanonical ensemble. KdV microcanonical is when instead of having exponent with chemical potentials, you say that you want all states E with the charges Q1 approximately equal to your value of Q1, and all charges of Q3 with the values approximately equal with your values of Q3. So it's sort of a generalization of a conventional microcanonical ensemble. Again, in the large C limit, you can calculate things explicitly, but then you have something like a phase transition. You have formula which you need to choose. You either use this formula or use this formula depending on your parameters. And of course, I will not discuss these formulas, but I will show you the plot that a naive analytic formula gives you this blue curve, but then you have a phase transition. And in fact, the correct behavior of the entropy is the blue line joined with the orange line. So the solid line is the correct behavior. So you can see something like a phase transition in your behavior of the Renyi entropy. And of course, you can see exactly this transition holographically because you have 2 subtle points. And that's exactly, and this point is exactly, this point is exactly when those 2 subtle point solutions have exactly the same free energy. And then if you change the fraction of the subsystem to the full system, that is a parameter f, one of the solutions or the other will win, and therefore you need to change the branch. So there are a lot of explicit results which you can get for microcanonical KdV ensemble and the generalized Gibbs ensemble if you do things holographically or if you work with large central charge where we have analytic control already from the CFT side. I think I should be wrapping up. I'll just mention that there's also interesting developments related to diagonal approximations on the holographic side. There was a paper recently where my understanding, the authors justify the diagonal approximation just from the holography point of view. I don't fully understand their logic. It's based on quantum information inequalities, but it would be very interesting to understand how that logic translates into field theory logic. And all the calculations you can do on the field theory side in a sister publication, we did holographically by just considering classical solution. So I'm skipping that, and this is my conclusion slide. In a nutshell, using the diagonal approximation, you can get a lot of explicit results for two-dimensional CFTs, and not only for the ensembles, which we already studied. For those ensembles, you almost for free recover correct results with very minimal amount of work, which tells you that this is a good start. And maybe if you can expand this approximation to include corrections, you can do beyond what was done before. But also for the novel ensembles, where you introduce KdV charges either through chemical potentials or through microcanonical, by just measuring the density of charge itself, you can get explicit results. It's very clear that the diagonal approximation is a versatile approach, and it will be very, very interesting to work out on the extensions. I think if one thinks seriously about the subsystem Hamiltonian and eigenstates of a subsystem, there should be a relation to the properties of OP coefficients. And there was a paper recently where people used the statistics of OP coefficients to say something about entropy. And I think there should be a relation between what we did, at least conceptually, and their approach. But I do not know how to do it rigorously. And I think that would be very interesting. And there are also other recent works, and I know that Sridip will be talking about that at this seminar very soon, about universality of vacuum entropy. And again, vacuum is difficult from our approach point of view because vacuum is a very non-chaotic state, and ETH usually breaks down for the vacuum. But there is some universality which people find in the CFT, so it will be interesting to see if the diagonal approximation can be used to understand that universality. And finally, it would be nice now to return back to the spin chains and maybe try to calculate some explicit results for systems like XXZ, which are very similar to two-dimensional CFTs, but a bit more complicated analytically. So that would be all I wanted to say today.